All right, new unit, exponential functions. Let's go to the first part of our lesson. Okay, we're going to start with characteristics of exponential functions. Investigating exponential functions of the form y equals cx, or most basic exponential functions. On the grid to the right, sketch and label the graphs as y equals 2 to the x, y equals 3 to the x, and y equals 5 to the x. Use the tables of values below and graphing calculator to assist you. So I'm going to fill in some values that you can use. Let me zoom in. Okay, so I have 0.1 repeating. Oh, sorry. For y equals 2 to the x, so for these coordinates, I've gone ahead and just found it on the graphing calculator. If you graph this, you can go to your table of values. So 1, 2, and then 2, 4. So these are for x values, okay? And then y equals 3 to the x, you can graph that. These are the values I got from my table of values. -1, 0.3, repeating, 0 and 1, 1 and 3, and 2 and 9. Okay, last one, y equals 5 to the x. Okay, let me just fill these in. Okay, let's go ahead and graph these. Okay, -2 and 0.25. Okay, so -2, 0.25. What am I doing here? We got -1, 0.5, 0, 1, 1, 2, and 2, 4. Okay, so what does that look like? Okay, nice as smooth as possible. There we go. Okay, next one in blue. -2, 0.1 repeating, so -2, 0.1 repeating. Oh, not a lot of space. It's right about there, really low. -1, 0.3 repeating, so a little bit underneath. Okay, 0 and 1, so 0 and 1, 1 and 3, and 2 and 9. 3, 8, 9, right there. So carefully draw this one. Whoa. Okay, there we go. Last one, -2 and 0.04, so even shallower. -1 and 0.2 right there. 0 and 1, and 2 and 1 and 5. 3, 4, 5. And then 2 and 25. And that would be all the way up here. Okay, there we go. All right, on to a few questions here. Use your previous knowledge of exponents to write the equation y equals 1/2 to the x with a base of 2. So I'll start with this, right? We know that number 2 in the denominator has an exponent of 1, so I can rewrite that as, using our negative exponent rule, 2 to the negative 1 to the x, and then I can use the product rule to multiply those two together, so y equals 2 to the negative x. Use your knowledge of transformations to predict how the graph of y equals 1/2 to the x compares to the graph of y equals 2 to the x. Use your calculator to confirm your prediction. Okay, so let me put these two equations or functions side by side. So our knowledge of transformations, right, when we're doing an operation on x here, and what's the only difference? The only difference is the negative value on the x. This is positive, this is negative, so that is a, when you put a negative in front, that is a reflection, right, about the y-axis. And is that what happens? So we're going to actually graph this, but let me write this out. So negative value on x will reflect the graph about the y-axis. And that's what we should expect based on our discussion of what we see here. Okay? So on the same grid above, sketch the graphs of y equals 1/2 x, y equals 1/3 to the x, and y equals 1/5 to the x. Okay, so we should expect them to be reflections of one another. So for the red one, just for contrast, I'm going to do a dotted line so we can see the contrast. Okay, so for y equals 1/2 to the x, the graph's going to look something like this. So it's going to reflect. So it's going to be there. And let's see. 1, 2, 3, 4, 5, 10, 15, 16. So 4, 6, negative 4, 16. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So right there. Okay, so roughly this is what it's going to look like. Okay, all right, for the blue one, y equals 1/3 to the x. So 1/3 to the x, we're going to expect it to go through this point right here. It's going to reflect this point across here. Okay, and it's going to go 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 2, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. So right about there. So what do we expect this to do? Something like this, okay? And then like that, okay? And the last one, y equals 1/5 to the x. Okay, let's take this point and let's reflect it across. So roughly it's going to look like, and let's reflect this one across as well. It's right there. So all the way down. Okay, and like that. Okay, you get the idea. So you can see that all three are reflections across the y-axis. Okay, what would the graph of y equals 1 to the x look like? Let's do a couple test values. So if x equals 1, then y equals 1. That's a horizontal line. Let's try y equals 1 to the third. Well, that's still y equals 1. So this is a horizontal line. So when the base here is 1, it's not really an exponential function. This is a linear function. Okay? So it's really not exponential when you have the base equal to 1. So it's a horizontal line. Number 6. What would the graph of y equals negative 2 to the x look like? Okay, so try to graph this on your calculator and then use the zoom decimal feature. This is for the TI-84. Does this graph appear to be continuous? Okay, let's just do a couple of evaluations here. If I do negative 2 to the 0, well, that's y equals 1. Okay, if I have x equal to 1/2, well, we know that's a square root, so what happens? That's y equals negative 2 to the 1/2. Well, that's y equals square root of negative 2. This is non-real. Here's another weird thing about this. If it's an even number for x, so x equals 2, so y equals negative 2 to the 2, that's y equals 4. If it's a negative exponent, so y equals negative 2 to the negative 3, well, that is 1 over negative 2 cubed, and that's 1/8. Sorry, that's negative 1/8. So this function is going to look super weird. It's going to look like this. So if you graph this, you're going to have a bunch of points here, and it's discontinuous. It's just a bunch of points on one side. So if the x value is positive, they'll be on the positive side. If the x value is negative, it'll be a discontinuous graph, so just a series of dots on the other side. So it's actually kind of a cool looking graph, but it's definitely not exponential. Okay? Not exponential. From the questions above, what are the restrictions on the value of the base? So the value of the base c, okay? So c, from what we just looked at here, c must be positive. So mathematically, how do we define that? C must be greater than 0, so cannot equal 0, right? And just to reiterate, if C is less than 0, what happens? So if I have my basic exponential function, right? Let's say C is less than 0. Let's pick negative 2. Well, this is from our previous graphing example. If x is a rational number, so if x equals 1/2, then here's the problem I run into. Well, that is a square root, and this is a non-real number. Okay, so not exponential. Okay, everyone. So from our class example 7.1, characteristics of exponential functions, we're investigating exponential functions of the form y equals c to the x. So what happens, so there's y equals 2 to the x. What happens when this value gets bigger, the c value? Well, let's see. We saw in the class example that it gets steeper. So when I do y equals 3 to the x, well, it gets steeper. Y equals 5 to the x, it gets steeper. Okay. We also investigated what happens when we have something like y equals 1/2 to the x. Well, we rewrote that as y equals negative, so y equals 2 to the negative x. So that is a reflection. So if we take this graph and we make the exponent negative, that's a reflection. That's a horizontal reflection in the y-axis. So watch this. Okay. So if I just turn this off, right, that's a reflection. Okay, so if I go like this, and I add a negative, that's a reflection. Okay, so likewise, that is also the same. So we just rewrite it as a c value. So when the c value is less than 1 but greater than 0, so in this case, it is a decreasing exponential function. Okay. So right here, as well as the base gets smaller and smaller, so closer to 0, okay, it gets steeper and steeper. So if I turn on all of them, well, that's what it looks like. Okay. And one last look with the c value slider. Okay, so when c is equal to 1, so this is where we say this is not even an exponential function, because if c is 1, it's just a horizontal line at y equal 1. So when c is greater than 1, it's an increasing function. Oops. When c is, so there we go. So c is 1. As soon as it gets bigger than 1, there's 2, c equals 3, c equals 5, and so on. It just keeps getting steeper and steeper. Okay? What happens when c is less than 1 but greater than 0? So c is less than 1. Well, it starts to turn into an decreasing function. So all the way down, when c is 0, what happens? It's just a horizontal line, right? Okay, so let's go over some definitions. Key characteristics. An exponential function models a type of nonlinear change. Exponential functions of the form, so this is the most basic, f of x equals c to the x, where c is greater than 0 and c does not equal 1. If c equals 1, then it's linear, right? So this graph has a characteristic where the y-intercept is always 1. There is no x-intercept. It passes through the point 1c, has a horizontal asymptote at y equals 0, so it approaches the line y equals 0 but never touches it. And here's the domain. All real numbers in the x, and then the range, y is greater than 0, so that's your horizontal asymptote. When c is greater than 1, here's the behavior. As the value of x increases, the value of y also increases. So this is what we saw, where the c value is greater than 1, right? And that's this series of graphs. As x increases, y increases. This is a growth function, so cells that divide and multiply. So cells that divide and they increase in number. When c is between 0 and 1, as the values of x increase, the values of y decrease. So we saw that in our exponential decay graphs, which are these three graphs. And these three would be values right here, where c is less than 1 but greater than 0. This is a decay function, so radioactive decay half-life is a great example of a decreasing or a exponential decay function. Okay, when we're determining an exponential functions from a graph, there's a couple ways we can do this. Okay, so we know this, right? For y equals c to the x, when x equals 1, the value of the function is c. So the ordered pair that can be formed is 1c. then you can determine the value of C and make the equation. So, and then to verify, you have to choose another point, okay, and then we substitute to verify that the equation is correct. Let's do a couple of examples. State an equation in the form y equals c to the x that can be used to describe each graph shown. So this one, there's our general format. If I have the point 1, 5, right? Let's verify this a couple of ways. 5 equals, so xy, 5 equals c to the 1. Well, 5 equals c. So of course, y equals 5 to the x would be our exponential function. Let's test it using another set of points, 2, 5. So test 225. So 25 equals 5 to the 2. 25 indeed equals 25, and that's a check. Okay. The other way you can look at this is a little quicker, is that's 1c, so c has to be 5. So right away, right, same as here, you can form your equation y equals 5 to the x. Okay. Next one. This is a exponential growth equation and a graph. This is decay, right? We know from our graphing earlier on in this lesson, this is a decay, and the telltale is that it goes this way. Okay, so we want it in this form. It's a decay, but we still want it in the form y equals c to the x. Okay, if we pick the point negative 1, 4, so let's do it a couple of ways. So negative 1, 4. Okay. A couple ways we can do this. Let's do it similar to the first part here. This is x, this is y. Let's plug in our values and solve for c. So y is 4, c is negative 1. Well, let's think about this. C to the negative 1, that's 1 over c. If we solve for c, right, let's just cross multiply. 4c equals 1, c equals 1/4. So our exponential decay becomes c value is 1/4 raised to the exponent x, right? And then if we verify this, folks, let's verify it with negative 216. So test negative 216. Okay, 16 equals 1 to the 4th to the negative 2. 16 equals, let's use properties of negative exponents. I'm going to do that. And then 16 indeed equals 16. The other way we can think about this is y equals c to the x. If I have negative 1 for y equals c to the x, right? We know 1c is how we form our equation and find the value for c. For exponential decay, instead of this, right, we know exponential decay has to show a negative exponent, right? So if we take negative 1, 4, right, instead of positive 1c, we're going to look at negative 1c, okay? So let's plug in 4 as our c value, right? We can say right away that the 4 is c because it follows this format. So y equals 4 to the negative x. Well, is that the same thing as what we had before? Let's check. Okay, 1 over 4 to the x. And that is indeed the same as what we had before. So hopefully this is a better explanation than the first time around. So please use this one when you're looking at making equations from graphs. Okay, last page. Application of an exponential function. A radioactive sample of radium has a half-life of 15 days. The mass m in grams in 15-day intervals can be modeled using the exponential decay shown. State the initial mass of radium-225 in the sample. Well, right here. 1.0 grams. What value does the mass of radium-225 remaining approach as time passes? So as t approaches infinity, mass m approaches 0 grams. Okay? Here's T. As mass goes down, what happens? As time goes up, mass goes down and it approaches 0. State the domain and range of this function. So domain is our time value. It has to be greater than 0. So it starts at 0, greater than 0. And that's it. So greater than or equals 0. And time is an element of any real numbers. Okay. Or in interval notation, 0, infinity. Range. Our mass, okay, it starts out, actually it starts out at 1, but the low value would be a mass of 0, so 0. And remember, it can't exactly equal 0, right? We assume it goes infinitesimally into the future. It'll never reach 0. Mass is an element of all real numbers, or 0, 1. State the exponential decay model that relates the mass of radium-225 remaining to time and 15-day intervals. Okay. Okay, let's build the equation like we did before. At t equals 1, m equals 0.5. So that is something right there on the graph. Y equals c to the x. So in this case, I have 1, 0.5. So I'm going to check. So there's my equation. I'm going to check 2 and 0.25. Okay, 0.25 equals 0.5 squared. And yes, indeed, that is true. Okay, determine how many days it would take radium-225 to decay to 1/30th of its original mass. Okay, so 1/30th of its original mass. We would have 1/30th of a gram at the end of that period, right? We're looking for how many days. So we have our exponential function here. The y value, this is what we have at the end, right? Our mass is our y value, so 1/30th, if I set it equal to 0.5 to the x. Okay, so at this point, we're not at a point where we know how to solve this algebraically. We're going to solve it graphically. So where is this 1/30th value? So that is roughly 0.03 repeating. So let's look for this on the y value. So this is going to be an approximation. So that's 0.1. So 0.03 would be about a third of the way down. So right about there. So this t value is about oh, let me rewrite that. Oops, sorry. To the t, that should be an exponent. That t value is going to be about 5. So t is going to be equal to about 4.9, or let's call it 5. Okay, remember this is in units of these are 15-day intervals, right? So So 15-day intervals. So that's 5 times 15 equals 75 days. So it will take 75 days to have 1/30th of a gram of radium-225 remaining. Hey everyone, let's continue with interpreting exponential equations, the intercepts and behavior, domain and range. So the goal here is, after learning about all the basic characteristics of your exponential functions, an increasing function and a decreasing one, can you kind of visualize this in your mind and answer some questions about the key characteristics without sketching? We'll do the sketch afterwards to verify. Okay, so let's try this. Y equals 4 to the x. Well, is that an increasing or a decreasing function? Well, that should tell you the C value is bigger than 0. It's greater than 0. Sorry, the C value is greater than 1. Okay, so that should tell you right away that this is an increasing function. So I'm going to just put that off to the side because we'll talk about increasing and decreasing later. X-intercepts, think about the characteristic of what happens here. Can y ever be 0? So can I raise 4 to whatever exponent and get a y value of 0? Because that's by definition what an x-intercept is. Well, no, of course it can't. So none. Okay. Y-intercept. Well, y-intercept is where x is 0. So when x is 0, well, 4 to the 0 is 1. So y-intercept is y equal 1. Okay, what's the domain? So if you think about the domain of our exponential function, well, it's going to be x such that x is an element of all real numbers, or using interval notation, negative to positive infinity. The range, okay, we know there is going to be, well, y could never be 0, right? But it's going to be greater than 0. Y such that, okay, so how do we write that in interval notation? Y such that y is greater than 0, y is an element of all real numbers, or round bracket 0 and then all the way to positive infinity. Okay, what about the end behavior? This is a little different than just talking about domain and range. End behavior, well, think about the opposite end, so the left end and the right end, right? So negative x, positive x. So if we think about y equals 4 to the x, think about what this does. So we can say it this way: as x approaches negative infinity, so we go to the left, y approaches 0. Okay? So think about the left side. It'll never touch 0, but y will approach 0 as x approaches negative infinity. You keep going more and more and more and more negative x. Okay? Let's go the other way. As x approaches positive infinity, well, y will also approach positive infinity. Okay? Is this an increasing or decreasing function? This is increasing. Okay? Now you can graph it. If I sketch this, what will this look like? Well, it'll look something like this. Okay? Where that's 0, 1. Okay, let's do the next one. Y equals 3 times 1/2 to the x. Well, where are the x-intercepts? So this is a very telltale decreasing exponential function. Okay? X-intercepts, there are none. Right? It's going to start really, really, really high up in the y values, it'll come sloping down, and as you go more and more positive x, it'll approach the horizontal asymptote y equals 0. Okay, so y-intercept, okay, if I plug a 0 in here, okay, let me back up to the x-intercept. I want to explain one more thing. You can ask it this way: will the exponential function ever touch the x-axis, right? So meaning, will y ever be 0? That's an x-intercept. So if you plug in 0 here, what value of x for an exponent will give you a y value of 0? Well, you can't. There's no such x value that will give you, there's no such x value for the exponent that will give you a y value of 0, so that's why there's no x-intercept. What about a y-intercept? Let's think the other way. X equals 0, well, y equals 3. Okay, 1/2 to the 0 is 1. 1 times 3 is 3. Domain, it's that classic, if you start from the left and go to the right, it's the classic like sloping ramp down. It's like a skateboard ramp, right? It starts really high, then slopes down as you go to the right. Okay, like a big curve. We'll sketch it. Okay, x such that x is an element of all real numbers, or negative infinity, positive infinity. What about the y values? Okay, it's still y such that y is greater than 0. Y is an element of all real numbers. So that's because of our horizontal asymptote at y equals 0. Okay, and the range is the same, 0, infinity. And behavior, as x approaches negative infinity, okay, so as we go more and more left, y approaches, well, it's going to be infinity. Okay, as x approaches positive infinity, so we're going to go to the left side and the right side, the end behaviors. What happens to the y value? Y approaches 0. Okay, and then our classic sketch, of this classic decreasing function. We said the y-intercept is 3, so it's going to go something like this, and then it's going to approach 0 as we go to the right. So this is 0, 3. Okay. Increase or decreasing? Obviously decreasing. Okay. Decreasing. All right. What this illustrates is the skill that you have to build to be able to interpret equations, functions, without sketching them. So the tendency or the temptation is to grab your graphing calculator, graph it so you can see it, then answer all these questions. Well, that's too easy, right? You want to challenge yourself by looking at the equation before you sketch it and just think and visualize what is happening and what are the key characteristics. You'll understand how these functions work, and when we move into the next lesson on transformations, even when you can visualize this or work this out in your brain before seeing a graph of it, it makes understanding these transformations and functions much, much easier. Okay, welcome back. Now we are looking at interpreting exponential equations, looking at intercepts and behavior, domain, and range. So in our class example, we had y equals 4 to the x. Well, does it have x-intercepts? No, clearly not, right? Y-intercept, yes, it has a y-intercept right at 1. Well, how do we know that? If we plug in a 0 for x, we'll get a y value of 1, so that's our y-intercept of 1. What's the domain? Well, it's x such that x is an element of all real numbers, goes negative infinity, positive infinity. Okay, what about the range? There's a horizontal asymptote at y equals 0, so it does not touch the y-axis. It does not touch the x-axis. There's no x-intercept, so it's y such that y is greater than or equal to 0. Okay, y is an element of all reals. end behavior as x approaches positive infinity. So as we go positive infinity, y approaches positive infinity. Okay, as x approaches negative infinity to the left, y approaches 0. It approaches the asymptote 0. Y equals 0. Okay, so that's that one. Contrast it with, contrast it with this one. So this is a decreasing function. X-intercepts, none. Y-intercept, if I plug in an x value of 0, I get a y value of 3. And so there's our y-intercept, 0, 3. Domain is x is an element of all real numbers. The range is y is greater than 0. Y is an element of all real numbers. End behavior as x approaches positive infinity, y approaches 0. It approaches that horizontal asymptote. As x approaches negative infinity, it approaches positive infinity for y value. So that's our end behavior. And of course, this is our decreasing function. Let me put both of them side by side. Class example. You can pause it here and give it a try. Okay. Okay. There you go. All right. Let's do some more of this visualization again without graphing the equation, right? Too easy if I let you use your graphing calculator and graph this. Um, let's do some graph matching. Here's a series of equations. Can you find which ones match which? Okay. So what's a good way to maybe use some process of elimination? I'm going to categorize it like this. This function decreases. Look at that c value, right? It's less than 1. This function decreases. Look at that c value, less than 1. This function increases. Look at that c value, greater than 1. Greater than 1 again, function increases, okay? We're using some of the skills or some of the examples that we saw before to help us answer this question. So I'm going to start with the increasing ones first, okay? Where are my two increasing ones? Right here and right here. Okay, so now we've cut our possible choices in half. These two are decreasing. We'll get to those, okay? Let's look at that y-intercept. That's a y-intercept of 2. Which one of these increasing functions has a y-intercept of 2? When I plug in x equals 0, well, 4 to the 0 is 1, and I'm left with y equals 2. So A must be Roman numeral number 4. Okay, so I'll put a big A right here. Okay, by process of elimination, but let's also just check it here. Roman numeral 2 must be B. Well, let's make sure. I might throw a different graph in there just to fool you, but you got to check. Okay, x equals 0. Well, 3 to the 0 is 1, times 4 is 4. Well, there it is. That's the y-intercept of 4. So this graph is B. Okay. All right, let's do the other two, which are the decreasing graphs. I have 3 times 0.2 to the x and 4 times 0.5 to the x. Well, again, the clue here is you're going to look at y-intercepts. You guessed it. So let's start with this one. When x equals 0, 0.5 to the 0 is 1, times 4 is 4. So which of these has a y-intercept of 4? Well, right here. This is a y-intercept of 3. This is a y-intercept of 4. Okay? So, equation number Roman numeral 3 is letter D. And I'll just label it up here with letter D. Okay. And lastly, let's just verify, well, process of elimination, but you still got to check. This is Roman numeral 1. If I plug in x equals 0, what do I get, folks? 0.2 to the 0 is 1, times 3 is 3. So that matches right there. Okay. All right, so that is letter C. And then I'm just going to fill this in. Key characteristics again, decreases. Okay, so when you're practicing this, be able to do this without reaching for your graphing calculator. When you write the diploma or unit test, you can certainly, no one's going to check, no one's going to know because you're allowed to use the graphing calculator. But a lot of these types of problems, there might be a whole bunch of them. And if you keep reaching for your graphing calculator to graph every single one of these, when in reality you can just take maybe 5-10 seconds and answer these questions pretty quickly, you'll save lots of time. If you try to use your graphing calculator for everything, you're gonna run out of time. Okay, is it increasing or decreasing function? So we did these examples in class where I gave you 4 equations and I gave you 4 graphs and asked you to match them, right? So process of elimination, 2 key characteristics. Look for the correct y-intercept and look for the shape of the graph. Is it increasing or decreasing? So if I take this first one, before I turn it on, right, I see the base is 0.2. So when the base is between 0 and 1, so greater than 0, less than 1, I know it's a decreasing function. So that's going to be a decreasing function. What's the y-intercept? If x is 0, the y-intercept is 3. So it's going to be here, and it's going to decrease, right? So let's turn that on. There it is, okay? How about the second one? Y equals 4 times 3 to the x. Well, I know because this base is this base is greater than 1 and the a value is positive, right? So this is going to be the increasing function. And if x is 0, the y-intercept is at 4. So it's going to go through 4, and it's going to be an increasing function. So let's take a look. Let's turn it on. Bam, there it is. Okay. Next one. A value is positive, but I have 0.5. The base is greater than 0, but less than 1. This is a decreasing function. If x is 0, the y-intercept is 4, so it's going to go through 4, and it's going to be decreasing. So let's see. There it is. Okay. And the last one, I have a value that's positive. Okay. The base is 4, so it's greater than 1. This is going to be an increasing function. When x is 0, the y-intercept is 2, so it's going to go through 2, and it's going to go increasing up. And there we go. Pause it here, give it a try. Okay. Come back. All right, folks, that's it for the you tried. Let's do this you tried challenger. Write the equation of an increasing exponential function which has a y-intercept of -6, a horizontal asymptote of y equals -7, and passes through the point 1, -3 in the form y equals cx plus k. Hint, y equals cx, there's no transformation, so start with that. That's your hint. Start with that as your base equation. Y equals c to the x, we know the characteristic. That is an increasing function, right? Because it says right there it's increasing. So if you start from there, right, let's think about a couple things. Y-intercept of -6 tells us that the graph was translated how many units down? We know this has a y-intercept of what, folks? What's that key characteristic of the classic increasing graph? Y equals 1, right? So it's been translated. If there's now a y-intercept of -6, well, how many units has it been translated down? It's been translated down, okay, 7 units. Before translating, right? So the original graph, y equals c to the x, we know the graph passed through 1c. That's just the basic characteristic. So a horizontal, it has a, so write the equation of an increasing exponential function which has a y-intercept of -6, a horizontal asymptote of -7, and passes through the point 1, -3. So 1, 3. Seven units up. So what's going on? So 1, -3. Oh, shoot. Oh, my bad. Write the equation of an increasing exponential function which has a y-intercept of -6, a horizontal asymptote of -7, and passes through the point 1, -3. Ah, okay. Okay, let me do this. Sorry about that. So I'm going to start here. So this is what it's saying. Y equals cx plus k. It has a point 1, -3. Okay. What is 1, -3 on the original graph y equals cx, right? So if we start at y equals cx and we translate 7 units down, we get to that. We get to y equals cx, c to the x plus k. So to get back this way, right, I'm going to add 7 units. So I'm going to go plus 7 units. So I'm translating back up to get to the original, okay, because it tells us we went down because of a y-intercept at -6, so I'm going to go plus 7 on the y value, okay? Plus 7 on the k value. So -3 plus 7 is 4, so it's 1, 4. So remember, this is in the format 1c, so therefore, the original function is y equals 4 to the x, okay? And then finally, if we translate 7 units down, right? This is this is a bit of an advanced problem. We haven't gone through transformations yet of exponential equations. That's next lesson, but this should make sense, right? 7 units down, well, y equals 4 to the x, and then I'm going to do a minus 7 for my k value. If you go ahead and graph y equals 4 to the x, and then graph this, you can check the 0.1, -3, and you can check the 0.14 using the trace function, and you'll see that it is 7 units translated down. Okay.